Assalamu alaikum wa rahmatullahi wa barakatuh. This is the first lesson in chapter 3. We will solve some problems about Newton's laws, and let's start with this one. Four forces are acting on a box as shown in the figure below. The net force on the box produces an acceleration. So the net force produces an acceleration of 1 meter per second square. What is the mass? So this is obvious that it's on the Newton's second law. And let's remember Newton's second law. Newton's second law says the net force acting on an object produces an acceleration. From the law, if net equals mass times acceleration, we can find the relation between the three variables. So here, let's calculate the net force. Sometimes the net force we write it down as F sub net, or we write it down as sigma F. So they are the same. And to calculate the net force, you need to calculate it in the x direction and also on the y direction. Let's calculate the net force on the x direction. On the x direction, that's the x direction. So the 2 Newton is positive, 5 Newton is opposite, so it's negative. So the net force here, sum of forces on x, equals 2 minus 5, so that's negative 3 Newton. And in the y direction, sum of forces in the y direction, here the y is upward, so it's 3 minus 3. And because the two forces are opposite and equal, so the net force here is 0, meaning that in the y direction, forces, we call it balanced force. So there is no acceleration. There is no acceleration in y direction. So the only acceleration here will be in the x direction. So let's substitute in Newton's second law, sum of the forces equals to the mass of the object, which I don't know, times the acceleration of the object, and he said here it's 1 meter per second square. 1 meter per second square. But because the net force here is negative, so the acceleration must have the same sign like the net force. So the acceleration and the net force, they must have the same sign. Both, if it is positive, so both will be positive. If it is negative, both will be negative. So negative 3 here equals to the mass times negative 1. Therefore, the mass is 3 over 1, which is 3 kilogram. Let's see something else. This one. The figure below shows a 5 kilogram block. So A. So the first one A, is 5 kilogram being pushed with a 3 Newton force. So you apply from your hand here, as you see here, you apply 3 Newton force. Of course, the red arrow, it says it's to the right. In front of this block, there is another 10 kilogram block B. The two blocks move together. So move together means they have the same acceleration. They have the same acceleration. How much force does block A exerts on block B? So he's asking here, what is the force between block A and block B? So you need to remember Newton's third law. If any two objects in contact with each other, A and B, so the first one applies a force on the other one, I will call it F. The other one, which is B, applies the same force on the first one. So the two forces here, they are equal and opposite. That's Newton's third law. So this is called the internal force between the two objects. The internal force between the two objects. He's asking here about this force F. How to find it? First, you need to work with the two objects as one big object. So I will draw the force diagram. That's the first one. That's the second one. The force diagram here is what? I have the weight of the first one, which is 5 kilogram times the gravity. So WA equals 5 times 9.8, gives you 49 Newton. Also, we have the second weight downward. So WB is 10 kilogram times the gravity, gives you 98 Newton. What else do we have? We have a normal reaction, which is upward, perpendicular to the surface. So I will call it here RA. I have another normal reaction on the other object. I will call it R sub B. And I have an external force coming from the right, 3 Newton. Do we have any other forces? Do we have friction? We don't have friction because here he says it's frictionless surface. So these are the forces that act on the object right now. So we need to find first the acceleration of the object. The acceleration of the object. Using Newton's second law, sum of the forces in the x direction equals mass times acceleration. What about the forces in the y direction? It's obvious here that the forces on the y direction are balanced. Why they are balanced? Because there is no motion in the y direction. The motion here is only in the x direction. The motion is in the x. But in the y direction, there is no motion. So the forces are balanced. What's the meaning of balanced here? Meaning that RA equals to WA. So it's 49 Newton. And RB equals to WB. So that's RB, which is 98 Newton. But here in this case, or in this problem, he didn't ask about the normal reaction A and the normal reaction at B. So here we will apply Newton's second law in the x direction. Sigma Fx equals mass times acceleration. What are the forces in the x direction here? We only find that there is only 3 Newton. So the 3 Newton, and it's positive because it's to the right, equals the mass, which is the mass of the total system, mass of both objects, which is 15 kilogram, times the acceleration. So the acceleration equals 3 over 15, which is 1 over 5, equals 0.2 meter per second square. So the first step is to find the acceleration of both objects. So the acceleration, which is 0.2 meter per second square, is the acceleration of A and also the acceleration of B, because he said here they are moving together. So the second step is to draw a force diagram for any of the two objects. Let's try to draw the free body diagram for object B. This is object B. And let's try to do it also for the other one and see what is the difference. This is object A. We have weight, which was like 98, like what we did before. Here we have weight, it's 49 Newton. Normal reaction, RB. Normal reaction, RA. External force, 3 Newton to the right. And here, because we separate the two objects, you need to draw the internal force that he was asking about, the internal force in between. What's the internal force here? From Newton's third law, it's two forces equal in magnitude and opposite in direction. So here, object A pushes object B with a force. I will call it force P. And also object B pushes the object A back with the same force P. So this is the internal force. We draw it here because we separate the two objects. And now we need to apply the same equation, Newton's second law. So we can apply it on the first object or the second object. They will give you the same answer exactly. Let's try to do them. Sum of forces in X equals mass times acceleration for object B. For object B. So what are the forces here in the X direction? You only find this force P. So P equals, the mass of this object is 10 kilogram. The acceleration of this object is 0.2. So that gives you 0.2 times 10 gives you 2 newtons. So the force in between the two objects is 2 newtons. If we try to find the result from the first object, sum of the forces for object A equals the mass of object A times the acceleration of object A. So what are the forces here on object A? There is a 3 Newton to the right, there is a P to the left. So it's 3 minus P equals the mass of this object, which is 5 kilograms. The acceleration of the object is 0.2. So if we try to solve this equation, 3 minus P equals 1. That means the force P is 2 Newton as well. So it gives you the same result. So if you try to find it from the first object or the second object, they must give you the same result. For this one, we have two objects here. They are related together. They have what we call dependent motion. The dependent motion is that if you try to move one object, it will affect the other object. If we try to move the object, the 100 kilogram downward, the object M will move upward. What's the relation between both of them? They have the same speed, but one is downward, the other one is upward. They have the same acceleration. One is downward, one is upward. They have the same distance. If you try to draw the 100 kilogram downward for 1 meter, I expect that the mass M will move upward for the same 1 meter. So what's important for me here is they have the same acceleration. Okay, let's read this problem together. The 100 kilogram block in the figure below takes 2 seconds to reach the floor after being released from rest. Released from rest means its initial speed is 0 from a height 1 meter. So now we have 3 information. We have the time of the movement, we have the initial speed of the movement, we have the distance of the movement. So we can use the first equation of motion. If you remember, we have 3 equations for the motion. Let us remember them. V equals VI plus AT. The final speed equals the initial speed plus the acceleration times time. You can add times if you like. The second equation, the distance or the height equals, some people they call it S, some people they call it H. It's up to you. So the h or the distance or the height equals vi times t, the initial speed times the time, plus half times acceleration times t square. I don't know why you always forget the square here. So please do not forget that t here is squared. The third one is v final square equals v initial square plus 2 times the acceleration a times the distance of movement, which I call it here h. So these are the 3 equations that I need for motion. In the previous problem, I have the time, I have the initial speed, and I have the height. And I need to find the acceleration, so I might use the second equation. I have the time, I have the initial speed, which was 0 by the way, and I have the distance h, so the only unknown here is a. Some people might ask, why don't we use the first one? The first one, you need the final speed, which we don't have it here. And also the last equation, the final speed is not known. So let's go back to the problem and try to solve it. First, I know that distance equals VIT plus half a t square. The distance is 1 meter. The initial speed is 0. Half times acceleration that I need. Time is 2 seconds. So 2 square. So that means 0 plus half times a times 4. Then you can simplify it. 4 over 2 gives you 2. So 1 equals a times 2. So 1 equals a times 2. That means the acceleration equals 1 over 2 or half meter per second square. So this is the acceleration of the first object, which is downward, and also the acceleration of the first object, which is upward. Let's call this one B, let's call this one A, so we can distinguish between each other. So this is the acceleration of the two objects. Now he's asking about what? What is the mass of the block on the left? To find the mass of the block on the left, you need to apply Newton's second law. Sum of the forces on the two objects equal to the mass of the two objects times the acceleration of the system. Here, to determine the forces, you need to draw free body diagram or force diagram. We have the weight of the first one, which is 100 times 9.8, gives you 980 Newton. You have also the weight of the first one, which is mass times 9.8. Maybe some people will ask, why don't you draw a friction? There is no friction because the object's in the air. There is also no normal reaction because there is no surface. What about the force in the rope, which we call it tension force? Here we don't draw the force in the rope because we consider it internal force. You can only draw it when you separate the two objects and when you draw a force diagram for the first one on its own or for the second one. But when you use the total system as what I did now, you do not draw the force in the rope. So I will draw the weight of the first one, the weight of the second one, and that's it. Then I will apply Newton's second law. Before you apply Newton's second law, you need to identify the positive direction of the forces. And the best way to identify the positive direction here is to use the direction of acceleration as the positive direction of the system. So what is the acceleration direction here? The acceleration moves in this direction, okay, and downward in the other direction. So this is the positive direction of the acceleration. That means what? That means for the 100 kilogram, the weight is in the same direction like acceleration. So I consider it positive force. For the other one, the mass is opposite to the direction of acceleration. That means it's a negative force. So when I substitute here in some of the forces, I will say 980, which is positive, minus mass times 9.8, which is negative, equals the total mass of the system, which is 100 plus m, times the acceleration of the system, which I found it here to be half. So this is the equation of Newton's second law. Let's simplify it. 980 minus 9.8 times m equals 100 times half gives you 50 plus 0.5 times m. Let's move the 0.5 m to the first side, and let's move, it's better to move the negative 9.8 to the second or to the right hand side and take the 50 to be negative 50 to the other side. So let's rewrite this equation again. 980 minus 50 equals 9.8 m plus 0.5 m. So 980 minus 50 gives you 930 equals, and 9.8 plus 0.5, that's 10.3 times m. So the mass m equals 930 divided by 10.3, and the result is 90.3 kilogram. So this is the mass of the objects, the mass of the second object. So I will choose number A. But let's ask ourselves another question. What is the tension? What is the tension in the rope here? The tension in the rope, the tension force. The tension force, as I said before, it's an internal force. But to find it, you need to separate the two objects. So let's try to separate the objects and draw a free body diagram for the first one or for the second one. Let's take the 100 kilogram object B. There is a weight downward, which is 980, and there is a tension force, which is a pull force, which is upward. So those are the only forces acting on the object. There is no friction because there is no surface. There is no normal reaction because there is no surface. What if we try to draw the free body diagram for the first one, the mass m? We will do the same. We have the weight, which is mass times 9.8. Take care that we know the mass now. It's 90.3 kilogram. And there is the same tension upward because it is the same rope. It is the same rope wrapped on the pulley. This is a pulley. Okay, so they have the same tension on the two sides. So we have here the free body diagram for both of them, so we can apply Newton's second law on the first one or on the second one, and they will give you the same result exactly. Sum of forces equals mass times acceleration. The force is here. Which one is positive and which one is negative? We said before, it's the direction of acceleration. If you apply it on this object, the acceleration is downward, so this is the positive direction. If you apply it on the first one, if you remember, the acceleration was upward. So this is the positive direction if you apply it on the mass m. Okay. So let's use this one, which is 100 kilogram. So 980 is positive. The tension here is negative. If you remember, the mass of the second object is 100 kilogram. 100. The acceleration of the second object is also 0.5 meter per second square. 0.5. So the tension is 980 minus 0.5 times 100 gives you 50. So minus 50. So the tension is 930 Newton. So this is the tension between the two objects, or the tension force in the rope. Okay. For this problem, a small car is pushing a larger truck that has a dead battery. So this car, number 1, pushes the truck number 2. The mass of the truck is greater than the mass of the car. The mass of the truck is greater than the mass of the car. Which of the following statements is true? The truck exerts the same amount of force on the car as the car exerts on the truck, meaning that the car pushes the truck in the point between them, this red point. The car pushes the truck with a force, and the truck pushes the car with the same force. Number B, the car exerts a force on the truck, but the truck doesn't exert a force on the car. Number C, the car exerts larger force on the truck than the truck exerts on the car. The car exerts more force on the truck. Number D, the truck exerts larger force on the car than the car exerts on the truck. And number E, the truck exerts a force on the car, but the car does not exert a force on the truck. Of course, from Newton's third law, if two objects are connected together, there is a connection between two objects, there should be a force in between. The first force, if you call it P, the second force, if you call it F, the two forces must equal in magnitude and opposite in direction. That's Newton's third law. Regardless of the direction of motion, regardless if there is acceleration or not, the force between the two cars, or the car and the truck, they are equal and opposite. So I would choose number A is the true answer. The truck exerts. Exerts mean like it does or it applies. The truck exerts the same amount of force on the car as the car exerts on the truck. This is the right answer. And as we said before, from this problem here, we found that the mass A, it exerts a force on B, which was 2 Newton here. And the mass B exerts a force on A, which is also 2 Newton. They apply the same force on each other, but in opposite direction. So let's go back to the problem here. But why the two cars, they move together? Because there is some external forces. The external forces coming from the tires of the car. This is friction force. This friction force is an external force. This external force causes the system to move and to have an acceleration. But for the force in between, there are two forces, equal and opposite. So Ahmed skydives, like he falls in the air, and parachutes from a stationary helicopter. So Ahmed moves with a parachute in the air. What's the acceleration of Ahmed when the air resistance equals twice the weight? So the forces affecting Ahmed are his weight, which is downward, and air resistance, which is upward. He mentions here that the air resistance equals twice the weight. Let's draw a free body diagram. That's the object. We have its weight, downward, and upward is the air resistance, which is 2 times W, or we can write it 2 times mg. So it looks like the total force is upward. That means the total acceleration also will be upward. Let's take it as our positive direction. Sum of the forces equal mass times acceleration. That means F air, the resistance of the air, minus the weight equals the mass of the object times the acceleration. The air resistance is 2 times m times g, minus the weight is mass times g, equals mass of the object times the acceleration of the object. We can remove mass with mass with mass. That means the acceleration of the object is 2g minus g. It gives you g, which is 9.8, and you assume that it was upward. So the acceleration is 9.8 upward. That doesn't mean that Ahmed is moving upward, but his acceleration is upward, while his direction of motion, it's obvious that he's moving downward. That means he is slowing down. Why he is slowing down? Because the direction of motion is downward, while his acceleration is in the opposite direction, and we know that when the velocity and acceleration are different in direction, the object is slowing down during this period. So I understand that I will choose number B. It's 9.8 meter per second square upward. Okay. After a skydiver has reaches his terminal velocity, and we know the terminal velocity is the maximum velocity that the object can reach while falling in the air under the effect of his weight and air resistance together. Then he opens his parachute. The air resistance is now 1,180 Newton. If the mass of the skydiver and his parachute is 80 kilogram, then find his acceleration. Let's draw the free body diagram. This is the object, and we know that the weight acts downward. That's W, which is 80 times 9.8. That's 784 Newton. 784 Newton. And we have also an upward force, which is the air resistance. And he mentioned here that it's 1,180 Newton. So this is the total force acting on the object. If you look here, the air resistance is greater than the weight, meaning that the net force is upward, and also the acceleration will be upward. So we can apply Newton's second law. Sum of forces equals mass times acceleration. We will take the upward as our positive direction. So I will take 1180 minus the weight 784 equals the mass of the object, which is 80 times acceleration. And then let's find the value of acceleration. So 1180 minus 784 divided by 80, that's 4.95 meter over second square. So this is the acceleration. As you assumed before, it's upward, so the right answer will be number A. Okay. Assume you are standing inside an elevator. In which of the following cases your weight will equal 0? And this is like a tricky question. So he's asking about the weight, and the weight does not change at all, because weight equals mass times gravity. That's called the real weight. And the real weight does not change at all, so none of those are right. Because he says here in which of the following cases your weight will equal to zero, will equal zero? And that doesn't make any sense because the weight is always mass times gravity. The other one, assume you are standing on a bathroom scale inside an elevator. In which of the following cases the reading of the scale will equal zero? So this is a different case. He's now asking about the reading of the scale. Okay, so you need to draw a free body diagram. We have the weight, W, equals mass times gravity. And we have the normal reaction of the scale. I will call it R. And the reading of the scale is this R. This normal reaction is the reading of the scale. So we have two cases here. We have two cases. Maybe the elevator is accelerating upward, and maybe the elevator is accelerating downward. Let's write down Newton's second law for both cases. In the first case, if the elevator accelerates upward, so the positive direction is the upward direction. So R minus W equals mass times acceleration. So the reading of the scale or the balance here equals W plus mass times acceleration. That means the reading equals to the weight plus another amount which is mass times acceleration. So the reading, excuse me. So the reading will be greater than the real weight. Let's see the second case. In the second case, when the elevator accelerates downward, let's take the positive direction, which is the direction of acceleration. And let's write down the equation of Newton's second law. Sum of forces equals mass times acceleration. In this case, the weight will be the positive one minus the normal reaction equals the mass of the object times the acceleration of the elevator. That means R, take it to the other side to be positive, and take the mass times acceleration to the first side to be negative. So it's W minus MA. This is the result. So the R equals W but minus some amount which is mass times acceleration. That means the weight, or R, is lower than the weight. So the reading of the scale will be lower than the real weight of the person. So let's go back to the problem. He says here, in which case the reading of the scale will equal to zero. The reading equals to zero. As you see here, R is lower than the weight. But in which case R will be zero? Look at this equation. R equals to zero when the W, that's right, when W equals to mass times acceleration. So W, which is mass times gravity, let me write it, mass times gravity, minus mass times acceleration will be zero. So mass times gravity equals to mass times acceleration. Remove the mass from each one. That means the acceleration of the elevator must equal the gravity acceleration. So the reading of the scale at this time will read zero when the acceleration of the elevator equals to the gravity acceleration. That means the object is under free fall. The object is under free fall. So let's read the statements here. The first statement, when the elevator accelerates upward, that's not right. When the elevator is in free fall, so this is the right one. The third one, when the elevator moves with constant velocity, that doesn't make sense. None of these is also not right. So I will choose when the acceleration of the elevator equals to g, means it's under free fall. As seen from above, a car rounds a curved path as shown in the figure below at constant speed. So the object moves in a curve at constant speed. Which direction best represents the direction of the net force acting on the car? The net force acting on the car. If the object is moving with a constant speed in a circle, the acceleration of the object is toward the center, and we call it centripetal acceleration. That means the net force will be in the same direction, and we call it centripetal force. So the net force is the centripetal force, and also it acts towards the center of the circle. So I will choose this one because this is the only one that goes toward the center of the curve. So I will choose number A. A car rounds a curve on a level road. The centripetal force on the car is provided by a rod in the shape of curve, and the car here is moving inside this curve on the road. He's asking the centripetal force on the car is provided by what kind of forces? The centripetal force here is provided by the friction between the tires and the road. The force between the tires of the car and the road. So it's the friction between the tires and the road. Not the inertia, not the gravity, of course. The force applied by the steering wheel doesn't make any sense. Okay? So this is the only force that is the centripetal force comes from the friction between the tires and the road. As baseball is being caught, its speed goes from 30 meter per second into 0 meter per second. So the speed changed from 30 meter per second to 0 meter per second in 0.005 seconds. So we can find the acceleration from these three information. I know the initial speed, 30 meter per second. I know the final speed is 0. I know the period equals 0.005 seconds. So I can use motion first law. V equals, or V final equals V initial plus AT. V final is 0, V initial is 30. Acceleration time is 0.005, so I can find the acceleration from here. 30 divided by 0.005, that's 6,000 meter per second square. Okay, if the mass, let's continue reading. If the mass of the baseball is 0.145 kilogram, how much force acts on it? We need to find the force acts on the object. So the force equals mass times acceleration. The mass, as he mentioned here, is 0.145, and the acceleration we just found it, 6,000. So let's calculate this one. 0.145 times the 6,000. It's 870 Newton. So the right one is number D. One kilogram object is moving west at a constant speed of 10 meter per second. So we have a mass, 1 kilogram, moving west at a speed 10 meter per second. A force of 100 Newton along the east direction is applied on that object. There is a force acts on this object to the east, which is 100 Newton. Is applied on the object for a time 0.01 seconds. So the time here, 0.01 second. The momentum of the object at the end of the 0.01 second is, and here we need to apply the equation of impulse and momentum. As you remember, we discussed this one in the lecture. The net force times the time, this is called the impulse, equals to the change in momentum, which is m times delta v, or as we said, m times v final minus m times v initial. Let's apply this equation on the information from the problem. So let's take the positive direction to be the right one, the east. So the 100 Newton is positive. So 100 Newton times the time, which is 0.01 second equals the mass of the object times v final, which is the momentum. This is the final momentum of the object. I will call it P final, minus, and this is actually what he's asking about. Find the momentum of the object at the end of the interval, minus the initial momentum, which is mass times velocity. The mass of the object is, yes, it's 1 kilogram, so it's 1 kilogram times the velocity of the object. He said that the velocity was 10 meter per second, but it's to the left. So the velocity is negative 10 meter per second. That means that's 10, and I will change this sign into positive. From here I can find the P final. 100 times 0.1 gives you 1, so that's 1. Take 1 times 10 to the other side, so it's minus 10, gives you negative 9. What is the unit for the momentum? Momentum is mass times velocity, so it's kilogram meter per second. So what's the meaning of negative here? Negative means it's moving to the left, or the momentum is to the left or to the west. So I will choose it's 9, but to the west. Okay, so that's the right answer. For this one, he's talking about the impact or the collision between two objects. And let's remember Newton's third law. If we have two objects and they are moving toward each other, or one is approaching the other, at a certain moment they will collide with each other. Let's say this is A and that's B. A was moving with a certain speed VA initial, and B was moving with a certain speed VB initial. So they will collide together, so they touches each other at a point. The collision time, it takes very short time, like milliseconds or so. So during the collision time, object A applies a force on object B, and object B applies a force on object A. What is the relation between the two forces? The two forces are equal in magnitude and opposite in direction. That's from Newton's third law. And if you remember the equation of impulse, the net force times time equals to m delta v, which is the change in momentum. So this one we call it the impulse, and this one is the change in momentum. So if the two forces are equal in magnitude and opposite in direction, so that means the net force here is 0. That means the impulse, this impulse, is 0. So the change in momentum also is 0. What the meaning the change in momentum is 0? There is no change. There is no change. Or we can rewrite it as the momentum at the beginning equals the momentum at the end. That's the meaning that the impulse is 0. There is no change in momentum. But for the collision here, the first force, let's call this is F1 and this is F2, which are equal and opposite. F1, it affects the object B. So because there is a force that acts on B, B will change its momentum. And also because F2 is affecting object A, A is also going to change its momentum. But overall, the total momentum before collision equals the total, let me erase this part, equal the total momentum after collision. And this is the equation of the collision. It's called the conservation of momentum. What's the meaning of conservation? Conservation means it's constant, it does not change, it's saved. So the conservation of momentum means the total momentum of the two objects before collision equal the total momentum of the two objects after collision. But for each object, there is a change in its momentum. Like object A, it changed its momentum, and object B also changed its momentum before and after. But for the total momentum, the total momentums, if we add momentum A to momentum B before collision, and if we do the same after collision, they have to be the same. There is no change. So let's say we have the speeds VAI before collision and VBI before collision. And after collision, let's say A is going to move back with a speed VA final. And also the object B will move back with a speed VB final. So let's write the equation of conservation of momentum in mathematical way. So the momentum is mass times velocity. So MA times VAI plus MB times VBI. So this is the momentum of the first one plus the momentum of the second one. So the two terms, that means the total momentum of the objects before collision equals the same but after collision. So it's MA times VA final plus MB times VB final. So this is the total momentum of the two objects after collision. They are the same exactly, but take care of something. VA and VB before and after, these are velocities, not speeds. So you need to take care of the sign. If the two objects, or if the object is moving to the right, it has a positive sign of the velocity. If the object is moving to the left, it has a negative sign of the velocity. Like in this case, VAI here in this drawing is positive, while VBI here it's negative. So you will change this sign and make it negative when you substitute in this equation. Okay? Also, for the speeds or for the velocities after collision, this one will be negative, while this one will be positive. So you just look at the problem and see the directions of the velocities, and you can substitute in this equation with the right sign. So let's go back to our problem and see how to solve it. A trolley A, this cart A, moves with 5 meters per second toward a trolley B. Moves, so this is the speed, 5 meters per second, and as you see it's to the right, so its momentum will be positive. Toward a trolley B of an equal mass. So he said here they have equal mass. So if you assume this one M, the other one is also M. Which is at rest. That means the initial speed of trolley B at the beginning is 0 because it was at rest. The trolleys stick together. Stick means they attach to each other. They hold each other. So they will move as one object after the collision. The trolleys stick together. That means they will have the same velocities. The same velocity after collision. And move off as one. So they moved as one object. What is their speed after they stuck together? Like find their speed after the collision. Let's write down the equation of conservation of momentum. MA VA initial plus MB VB initial equals MA VA final plus MB VB final. And let's substitute. MA is M. He didn't give us the M, but we said it's M. Times VA initial, which is 5. So M times 5. Plus the second momentum, he said it was at rest, so this is 0, equals, after momentum they got stuck together. That means they have the same final velocity, so I will take it as a common factor. So the rest is MA, which is M, plus MB, which is the same M, times V final. I would call it V final, not VA or VB. It's only V final. They have the same velocity. That means it's 2 times M times V final. From this equation, we can remove, like it's obvious here, it's very clear, we can remove this M with this M. So V final equals 5 over 2. We will take the 2 to the other side. We divide over the 2. So it's 5 over 2 gives you 2.5 meter per second. So the velocity is 2.5 meter per second. And the sign of the velocity is positive, means it's moving to the right. So both of the objects will move to the right, and he showed us this part in the drawing here. So I will choose number C, 2.5 meter per second.